Okay, let's take a look at slope fields, and I'll kind of just work you through 6 different examples. This first one, it says dy dx equals to 2. Okay, again, this is a differential equation that describes the slope in this case. All of these are already solved for dy dx. That's not the only way a differential equation can present itself, but these are kind of the easier examples. So if you have dy dx equals to 2, it means the slope is always 2. So if you took all these coordinate points, all these grid points, and you kind of graphed a little bitty line here, you'd graph every point no matter where it is. Whether you're looking at 0, 0, the slope would be 2. 1 comma, slope 2, slope 2, slope 2, slope 2. So no matter where I am here, it's independent of x and y. It would look something like this if we filled this whole thing out. No matter what x and y are in the grid, we always just have a slope equal to 2. That's what it looks like. And so some sort of solution curve in that slope field, well, if you told me some initial value, so you knew that this value was on your graph, well, then the solution would follow the slope field. There's the solution curve through the slope field. If you told me that it was over here, well, then it would follow the slope field over here. And again, all the solutions have a slope of 2. And that's what this restriction is saying. The slope is always 2. All right, let's look at this one. This is more interesting because now the slope is dependent on x. Okay, so if x is 0, what's the slope? Well, the slope is just 0. So let's do all those. So x is 0 here, x is 0 at this point, x is 0 over here. All right, when x is 0, the slope is 0. Well, what happens if, let me think. How about if x is equal, oh, I totally jacked that up. Well, good thing I can just highlight this. That was a y equals to 0. That was really bad. I'm not going to do that over here. Just look at that, color it in. Boom. Okay. X is 0 here, there, right? X is 0 there, and then we have a slope of 0. All right. Now what happens if x is 1? Well, x is 1 on this line. So when x is 1, the slope is just 1. It just corresponds to x value. It's got no dependence on the y value. So let's draw a slope of 1 when x is equal to 1. And then when x is 2, it's going to have a slope of 2, so it's steeper here. When x is negative 1 over here, well, it's going to have a slope of negative 1. And then it would be negative 2 when x is negative 2. And it would look something like that. And if you can imagine here, take some solution curve. Let's say we know it goes through this point. Then it would go something like that. And hopefully you can imagine that if the derivative, the slope, is equal to x, then the function is some quadratic. Just like if the derivative is equal to 2, the function is some line. Okay, so hopefully we're starting to match the slope field to the differential equation to the actual function. All right, let's do the reverse here. Now, the differential equation says dy dx equals to y. So whenever y is equal to 0, and that's what I was doing over there, then when y equals 0, we have a slope of 0. So let's do that. So we have that. And when, okay, let's make y equal to 1. We get a slope of 1. So when y is equal to 1, we get a slope of 1. When y is negative 1, we get a slope of negative 1. When y is 2, right, all of these, we're going to have a slope of 2. Okay, now let's make y negative 2, so we have a steeper negative slope. And it would look something like that. Okay, does that make sense? Again, the slope is dependent on y. These are kind of the easy cases, then down here we have more complicated versions. Okay, so now the dy dx is equal to x plus y. All right, well, let's do some easy ones. Well, when x and y are both 0, then we still just get a slope of 0. And let's go up here. This is when x is 0 and y is 1. Well, 0 plus 1 is 1, so let's draw a slope of 1. Let's let x still stay be 0 and y be 2, so I need to get steeper. Okay? How about over here? When x is 1 and y is 0, that's a slope of 1. What about here? Well, what happens? The x is 0, y is negative 1, so that's a negative 1 slope, and then a negative 2 slope. You can kind of see the pattern here. What if x and y are both 1 at 1 comma 1? Well, then it's a slope of 2. Then it'll be a slope of 3. You can just keep kind of seeing what happens here. If I go further this way, now I get a slope of 2, and then a slope of 3 if I increase x. Okay, and what about here? what's here? That's when x is 1 and y is negative 1. That's a slope of 0. What happens if I'm at 2, negative 2? Slope of 0. What happens if I'm at negative 1, 1, 0? And you can kind of see there's this pattern here which corresponds to the line y equals negative x. You can see that if y equals negative x, this is always going to be 0, and you can start to see this pattern. Again, you can pick any x value and any y value you want. So like here, negative 1 comma negative 1, that's going to be a slope of negative 2. This is negative 1, negative 2, so it's a slope of negative 3. You can kind of start to fill out this whole thing. Take your time, fill out the whole thing if you want. Let's look over here. If y is 0 and x is 0, well, 0 minus 2 times 0 is 0, so that's still 0. How about x is 1 and y, if x is 1 and y is 0, so that'd be a negative 2 slope. Negative 2 slope. Okay, what about if we're up here? X is 0, y is 1. We get a slope of 1. If we're down here, x is 0, y is negative 1. Negative 1 slope. So you can plot these as many points as you want. The AP usually has you do like 6 of them. You usually don't have to do 20 of them or so. Plot as many as you want. Go here, negative 1, negative 1. So x is negative 1 to make this 2. Y is 1, so that's going to be a slope of 3 right there. What about here? This is an x value of negative 1 and a y value of 0, so it's a slope of 2. Here, this is an x value of negative 1 and a y value of negative 1, so it's a negative 1. And then down here, you get 0. Okay, you can kind of see what does this form. Well, when y equals 2x, the line y equals 2x, this line right here, everything on there will have a slope of 0. Again, you could go 1 over and 2 up. Up here, you're also going to have a slope of 0, right? Because when x is 1 and y is 2, that produces a slope of 0. So you can start to see patterns of where these horizontal lines are. Horizontal lines, horizontal lines. Okay, this one's kind of cool, and this will be my last one. Slope fields are pretty easy. They're kind of robotic in terms of you just plug in what x is and what y is, figure out what the slope is, and once you know the slope, then you can kind of draw some segment to tell you what that is. All right, how about this one? So what does this predict the slope is if x is 0? Well, if x is 0, it's going to make this fraction 0. So anytime we're at 0, let's do that. But I can't make a mark when y equals 0 because 0, 0 doesn't exist in this case. So don't put anything there. Well, what happens if y is equal to 0? Well, if y is equal to 0, I have an undefined thing, but really undefined slope is a vertical slope. So let's put a vertical line there. And I'm doing this, hopefully you'll end up seeing a picture. Okay, what happens when x and y are the same, right? I'm at 45 degrees, so like I'm at 1 comma 1. Negative 1 over 1 is a negative 1 slope. Well, what if I'm down here and x is negative 1 and y is negative 1? Well, I get the same thing. Negative 1 over negative 1, and a negative is a negative slope. What if I'm here at like 1 comma negative 1? 1, negative 1, negative. That's going to be a positive 1 slope and a positive 1 slope. And hopefully you can see that it didn't matter how far it went out. I could have been at 1, 1, or it could have been at 2, 2. I could have been at negative 2, negative 2. I could have been at negative 2, 2, and I'm still going to get these same things. Anytime x is 0, I'm going to get those horizontal. If x is 0, I get a slope of 0. If y is 0, I get this, and look what that slope field turns out to be. The slope field describes a solution curve that's a circle. Okay, and in probably the previous video, I took this differential equation, which is a separable differential equation. I separated and integrated, and then I got the equation for a circle. Just to remind you, when you separate and solve this, you'll get something that looks like this. This r is going to be dependent on your initial value. Again, I just kind of took 6 different slope fields and kind of just went through. I drew solution curve through this, and again, you can draw a solution curve through any of them. These are going to be a little more complicated to draw a solution curve through. I can pick anything right here. Let's say I have that I know that point exists. Let's say I knew the point negative 3 comma 0 existed on the graph, then this blue dotted line would be the solution curve. It follows the slope field because the slope field is describing the slope at any point of your function. But if you take a function and you draw enough little bitty lines here, right? You can now claim that this parabola is just a ton of little bitty line segments instead of these very discrete things. Okay, so that's subfields.